Okay. Hello, everyone. Welcome to session 3 for day 2 of PyCon Indonesia 2021. My name is Hardeva, but you can call me Deva, and I will be the moderator for this session. In this session, I would like to introduce our speaker, Mrs. Alicia Frame. Alicia is the Director of Product Management on Data Science from Neo4j. The talks that Alicia will deliver is titled Graph Embeddings, Secret Ingredients for Relationship-Driven AI. This will be a rather unique session with no Q&A session. Therefore, if you have any questions, feel free to reach out to Alicia via PyCon website. Okay, without further ado, I present to you Alicia Frame.
Thank you for joining us, and I'm super excited to get to talk not just about Neo4j, but also about one of my favorite technical topics, and something that I think will make a lot of people's lives easier, will help you make sense of your connected data, and will help you kind of get all the promised value of graph really quickly. And so in this webinar, we're going to be talking about graph embeddings, what they are, what they're good for, why you should care, and we're going to do a demo. So to provide an overview, the first section of this deck is just a product overview. So what's a labeled property graph? What's Neo4j? What do we offer for data scientists? If you've seen our talks before, this is where you can go get a cup of coffee. The second section is going to be about graph embeddings. Let's start from the basics. What are they? What are they useful for? And why should you care? Then we're going to talk about graph embeddings in Neo4j, the techniques we offer, how they work, and what they encode. And then finally, we're going to move on to a really fun demo, generating some graph embeddings in Neo4j and using those for real-time recommendations. So let's get started. If this is your first Neo4j webinar, if this is your first time joining us, welcome. We're glad to have you. And if you haven't heard of us before, we are the connected data company. Neo4j invented the concept of the labeled property graph, which is how we store our data. We offer the world's leading graph database. We offer the most flexible graph data model that's out there. We introduced the easiest to use graph query language with Cypher. And 2 years ago, we were the first company to offer the Graph Data Science Library, or really an enterprise-ready product for data scientists to make sense of their connected data. Thousands of companies, hundreds of thousands of folks use Neo4j to get value from their connected data. So whenever I talk about this, especially with data scientists, I like to start off with just basic concepts like what's a graph? And sometimes when you're, especially in data science world, when you talk about graphs, sometimes people think of charts. When we at Neo4j or in the graph data science community say graph, what we mean is a labeled property graph. And you can think of it as just a different way of representing your data. In a graph, your nodes are your nouns. So in this example, your nodes are people and cars. They represent entities. And then your relationships are how they're connected to each other. So here you have Andre loves Mika, Andre drives a Volvo. Those are how your nouns are connected to each other. They're the verbs in our data. And then you can have properties that describe those nodes or the relationships. So Andre is the name of a person node. The brand of our car node is a Volvo. The drives relationship has a label of since January 10th, 2011. So when you think about it as nouns and verbs and then everything that describes them, you realize you can encode a lot of data as a graph. And graphs are a really faithful representation of your data. Conceptually, in the real world, how your data exists is there's a lot of connections with it, and graphs treat those as first-class citizens. So once you start thinking about graphs, you realize a lot of things are graphs, right? Everything is naturally connected. When people talk about the history of graph data science, graph algorithms, historically, people go back to networks of people. You have social networks, you have people who are friends with each other, you have employers who have employees, customers, suppliers, what have you. But you're talking about social interactions, social networks, and who knows who, right? As you build on that with more sophistication, we start talking about transaction networks. So we take our people and we add in items. This person bought this item, they viewed this item, they returned this item. And when you add items or kind of physical things into that social network, you have a transaction network. These are frequently used in payments, retail, supply chains, risk management to represent how items get to customers, how customers purchase items, and how items move throughout the supply chain. Getting even more sophisticated or kind of more generalizable, we talk about knowledge networks or knowledge graphs. And what a knowledge graph is it's just a map of heterogeneous concepts. So people, places, things. In this example, we've got people, sports, countries, different concepts connected to each other based on how they're related. And a knowledge graph can represent anything really. It's just facts and how they're related to each other. When you represent your data as a knowledge graph, you're able to capture how all of these disparate concepts are connected to each other, and kind of your conceptual model or your whiteboard model becomes your data model. And so when you talk about your business or the problems that you're actually facing, when you think about, what drives your business, you think about nodes, right? Employees, citizens, customers, products, plants, warehouses, suppliers, distributors, partners, right? But on its own, those are meaningless. In order to make sense of your data, in order to understand your data, you need the relationships between those nodes, right? You need employers are employed at this plant or employed by this company. You need this factory manufactures this part. This part is shipped to this warehouse. This warehouse distributes this product to this store, right? Without those connections, without those verbs, your data is meaningless. In order to understand what drives your business, you need the connections, the relationships within your data sets. And because of that kind of conceptual model, where you realize that the relationships, the connections within your data are what's really important, more and more people are realizing this. Last year, Gartner said that graphs form the foundation of modern data and analytics because they can really faithfully represent your data. They're really important for machine learning, explainable AI. And we've seen kind of at the same time as that, graph techniques are growing in prevalence in industry. As AI maturity grows, we see much more adoption of graph techniques. This has been paired with a similar uptick in interest in academia. So if we look at the number of publications on graph, it's gone from just over 200 10 years ago to over 6,500 last year. Industry analysts realize graph is important. Academics realize graph is important. And Neo4j really serves the purpose of translating those cutting edge state of the science concepts that are in all of those publications into techniques that you and folks in your industry, your peers, can use right off the shelf. And because of that, we've seen tremendous interest in our offerings. We have over 200,000 downloads of our graph algorithms book. We've seen a massive increase in traffic around data science on our web pages. We actually have over 100,000 practicing data scientists, including all of you, who are engaging with Neo4j on a daily basis. So what do you do with graphs and data science? Hopefully I've convinced you that relationships or connections are important. When we talk about graphs and data science, if data science is just answering questions with data, graph data science is just using the connections or the relationships within your data to answer questions. And when you do graph data science, you might be using queries. So this is if you've used Neo4j before, if you've used Cypher. A query is how you find a pattern that you know exists in your data. So let's say I'm a fraud investigator. A query might be saying, find me everyone within 3 hops of this account that I know has committed fraud. I know what I'm looking for, and I use a query to find it. Machine learning is where you're uncovering trends or you're making predictions about your data based on your graph structure. That's where graph algorithms as well as graph machine learning fit in. And then visualization is kind of that third pillar where I need to explain my findings, I need to collaborate with my team, and I need to make sense of my data. And this is where I'm going to visualize, explore, collaborate with what I've got. And so if you take all of this together, queries can be used for data exploration. They can be used for feature engineering. Machine learning algorithms can generate really useful features or be used for analytics. And visualization might be how you explain your analytics dashboard or how you interact with your data to explore it. And all of that together is graph data science. When we talk about how you actually do graph data science, we really think of it as kind of a series of steps. The foundation is representing your connected data in a connected shape. So this is where you get your data into a graph, you build your knowledge graph where you're linking all of those concepts together. And you can start off with queries to find the patterns you know you're looking for in connected data. As you get more sophisticated, as you start to want to use more ML techniques, this is where we talk about graph algorithms. So you're using unsupervised machine learning techniques to find patterns, associations, anomalies, and trends. It's where you say, okay, fine, I have 1 billion nodes, I have 10 billion relationships. What's important? What should I be looking at? The algorithms are unsupervised techniques that help you sift through that data and figure out what's most important, where should I be paying attention, or what's unusual. And then as you get more sophisticated, as you have labeled data, that's where we talk about moving into graph machine learning. This is where you use algorithms or embeddings to generate predictive features that you can add to your machine learning pipelines, and you don't have to even know what you're looking for yet. Once you've done that, you can train in-graph machine learning models to predict missing data or how your graph structure will change in the future. Each of these steps kind of builds on the previous step. Each one is valuable, and each one answers really distinct questions. So how do you do all of this? I'm here from Neo4j to tell you that we've really worked super hard on building a solution to this. Our graph data science platform consists of our database, which lets you store your connected data in a connected shape. So you can query it, persist it, it's there, it's in the right format to interact with. On top of that, you might run the Graph Data Science Library, which is what I work on. And that's kind of our scalable graph algorithms and machine learning techniques. This is how you can rapidly analyze and do data science on your massive data sets. And then finally, we talk about Neo4j Bloom, which is our visualization platform. This lets you explore your data, collaborate with teams, make sense of what you found. And if you think back to that 3-circle Venn diagram from a couple minutes ago, the database is our queries, data science library is our algorithms, and then Bloom is our tool for visualization. When we talk about the Graph Data Science Library, we're really talking about 2 things. The first, and I think what most people think of, is graph algorithms and machine learning methods. The Graph Data Science Library includes, I think, over 65 different algorithms. They scale into the tens of billions of nodes, and they're all about making sense of your data. We also offer our analytics workspace. And so what that is basically the tooling to take your underlying data in your database, select what you want to do data science on, transform it, layer it, and make sense of it. This is all optimized for global traversals. It lets you store predictive models in our model catalog, and it's really about enabling you to do data science at scale. When we talk about the Graph Data Science Library, what algorithms we have on offer, we typically break it down into the unsupervised graph algorithms, where you don't necessarily need labeled data. This is things like clustering, association, and dimensionality reduction. And the supervised machine learning algorithms. And these are about using your graph structure as your labeled data and making predictions. In this webinar, we're going to be talking about graph embeddings. And what graph embeddings are is they're basically a technique for dimensionality reduction that let you figure out, given all of the data in my graph, what are the features I need to be able to do machine learning. So let's talk about graph embeddings. What the heck are they, and why should you care? So whenever someone presents me with a new concept, I usually start with Google. If you Google what is a graph embedding, you're going to get some answers that may or may not make sense. So Google will tell you an embedding is a relatively low dimensional space into which you can translate high dimensional vectors. Okay, Wikipedia maybe makes a little more sense. In mathematics, an embedding is one instance of some mathematical structure contained within another instance, such as a group that is a subgroup. I'm confused, Brittany's confused. What are we talking about? So let's think of it this way. An embedding is a way of mapping something complicated, so a document, an image, a graph, into something simpler. Maybe a simpler way of thinking about it is, how do you embed a person? So what's an embedding? You can think of it as, I'm me. I could embed myself, three-dimensional, moving, talking me, into 2 dimensions in a portrait. And a portrait embeds me into a 2-dimensional representation. But what's really important with your embedding is it should be a simplified representation, so simpler than the most complicated thing, but it should still be recognizable. So if I have 3 potential examples of embeddings, I've got a photo of me, I've got a lower dimensional representation, but I think we can still tell that's me. And then I've got a super pixelated blob. And so all of these are lower dimensional than me talking to you right now, but which one is a useful embedding? So if we think about it, the first one is too complex, right? There's a lot of colors, there's a lot of pixels, there's a lot of information. But the blob that's all the way on the right is probably too simplified. If I just gave you that, you wouldn't necessarily know it's a photo of me. So it's kind of like a Goldilocks problem. The best embedding is the simplified representation that is still recognizable and should still be usable. So I can take all the complication that's me talking and moving and existing in time and space, condense it into a portrait, and the best embedding, the best simplification of me is the one that's still recognizable, but is as small as possible. So if we think about that, with a graph, an embedding takes your complicated graph, so I've got a graph on the left, and it translates it into something simple. And in order to be useful, it has to preserve key features, reduce dimensionality, and still be able to encode the graph structure. So if I take my full graph, maybe I've got 100 nodes. I want to encode that graph in something smaller. So the raw encoding is I have 100 by 100 matrix. And first I can encode my first degree neighbors. So are these 2 nodes 1 and 2? Are they connected to each other? 0, 1. And I have 100 by 100 matrix. But in order to capture the graph, I need to also capture, are they next to each other at 2 hops? Are they next to each other at 3 hops? Etc., etc. So now I have a massive data structure. That's a very high-res portrait. Then what I need to do is condense all of that information down into something much simpler. It's got the important parts. It's got the features I need in order to know these 2 nodes are different, these 2 nodes are close to each other, but it doesn't have all that extraneous information. So maybe I have 20 numbers that represents every node instead of n 100 by 100 matrices. And to measure if it's useful or not, I have to know if I can use it to preserve those key features, if it's smaller, and if I can still reconstruct my original graph from it. So a graph embedding can represent different aspects of my graph, right? I can have a node embedding, which is kind of what we do in Neo4j. This describes each node. Each node gets a bunch of numbers. Each node gets a portrait of itself that can be used for machine learning. Other types of embeddings that exist in the world are edge embeddings or relationship embeddings, where you're creating a representation of every connection. You can have path embeddings that represent traversals through your graph. You can have subgraph embeddings, where instead of describing every node, maybe I have some numbers that describe every community. Or I could have a full graph embedding that encodes my entire graph into a single vector. So at the bottom of this slide, I've got an example. You've got an input graph, and you can translate it into different types of embeddings. And each one of them looks different in embedded space. A node embedding creates a representation for each node. An edge embedding creates a representation for each edge. So in my graph, I've got 9 nodes, and I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 relationships. Those are reflected there. If I want to use a substructure embedding or a subgraph embedding, I've got 3 communities. I've got 3 community embeddings. Or if I create a whole graph embedding, that's just one for that example graph. So each of these is useful for a different problem, and you might want to choose the most important one. In general, the most useful embedding is a node embedding, and that's what we offer in Neo4j. So why do you need them? What are they good for? I've told you can make a simpler representation of your graph. It should be able to be decoded. Why do you care? What are they useful for? The idea is that a graph embedding takes your graph, translates it into meaningful numbers that you can then use as inputs for downstream tasks. So maybe you have a machine learning pipeline and you need to encode all of that complicated information from your graph into a bunch of numbers. Or maybe you want to visualize your graph, not as this big balloon visualization, but maybe as a simple 2D plot. You can use an embedding for that. Or maybe you just want to know how similar are two nodes, and someone told you node similarity would take too long to run on your graph. You can use an embedding for that. So kind of substituting in some examples, if you want to say, okay, I want to reconstruct the structure of my graph. I want to make a prediction about links in the future. Well, that could be a recommendation problem. If I want to use my embedding and I want to classify nodes, I want to figure out which node is which. Well, maybe I've got a graph and I want to classify which accounts are committing fraud. If I want to take my embedding and I want to do visualizations, maybe I've got a data set around patient journeys and people's symptoms, and I want to be able to cluster nodes that look like sick patients separately from nodes that look like healthy patients. So, title of this webinar might have given it away, but graph embeddings are kind of the secret ingredient to be able to use your complicated, rich graph data in traditional ML techniques. And you might be like, cool, graph embeddings, amazing. I don't ever need anything else again. So I like to kind of include the slide that's like, how do I pick queries, algorithms, or embeddings? Queries are great when you know exactly what you're looking for. You need something human readable as a result, and you can describe the pattern. So if I'm looking for fraud and I say, okay, people are likely to commit fraud if they have over $1 million of transactions, they're within 3 hops of a fraudster, and they have at least 2 deposits in the last 3 days. That's a cipher query. I know what I'm looking for. I can match it. A graph algorithm is going to be useful when I know the kind of pattern I'm looking for. So I want to figure out who I want to market to. And the person I want to market to is someone who's really important. So I could use a centrality algorithm. I know the type of pattern I'm looking for, and I can use the result directly. So who's most important? This node in my graph is most important, market to them. Embeddings are useful when you know there's something important in your graph, but you don't know exactly what the pattern you're looking for is. You don't know if it's centrality, communities, similarity, you don't know, but you just know the graph structure is useful. And what it gives you is a highly predictive numerical representation of your graph that may not be human readable. So what you need is a downstream task like visualization, prediction, classification that you can then use that output in. So now you're all experts on graph embeddings. How do you do those in Neo4j? We offer 3 techniques: FastRP, Node2vec, and GraphSAGE. All of them are node embeddings. So all of them create representations, numerical representations of the nodes in your graph that you can use for a downstream task. The difference between them is basically how they make the predictions or how they generate the embeddings and the types of graph that they can use. So FastRP, far and away the fastest, works on directed graphs, weighted graphs, node properties with a little bit of finessing. You can use it on node labels. That's usually the one we recommend you start with. Node2vec is probably the most widely known. It's really easy to understand how it works. The hyperparameters are useful. Doesn't support properties or labels, but it's a good one to kind of conceptually wrap your head around. And then GraphSAGE is really cool because it creates an inductive model. It uses a graph neural network, and it gives you a predictive model that you can apply to new data. It's an inductive embedding. And so in the next section, I'm going to kind of walk through each of these, and then Zach is going to join us to give you a quick demo. So let's start off with fast random predictions, or FastRP. This works via basic linear algebra, and it's the Johnson-Lindenstrauss lemma. And what this says is if you take a matrix and you multiply it by an appropriate matrix that's in a lower dimensional space, you can preserve the distance between two nodes or two entries in your matrix in a lower dimensional space. So you take that adjacency matrix we talked about, 100 node graph, 100 by 100 adjacency matrix, multiply it by a special matrix. This is our random projection, and you get a lower dimensional space. So this is your like m by m matrix times an m by n matrix gives you an m by n output, remembering linear algebra. And in each iteration, as you keep going with the algorithm, you construct an intermediate embedding by averaging the intermediate embeddings of neighbors from the last iteration or your initial random vector. So basically, you take your adjacency matrix, multiply it by a random vector or your previous step until you get a representative sample. What's really cool about FastRP is the number of iterations, so how long it runs for, determines how large a neighborhood around each node you're sampling for your embedding. So the larger number of iterations, the further out in your graph you're searching to come up with a representation. And so with that, I'm going to, it can also encode node properties and weights. And so properties can be specified as feature properties. Their influence is determined with property dimension. Node embeddings are constructed in basically the same way. You're concatenating a topological embedding, so that's the one we just talked about, with a property embedding that describes your node properties. And the properties are embedded in the same way as the graph topology is. The node properties get initialized with a random vector. At each iteration, they're being averaged with the node properties of neighboring nodes. So then you end up with your topological embedding, your node property embedding, and you're able to represent both in your embedding. And if you're still kind of struggling to wrap your head around it, I'm going to pass it off to my colleague Zach, who's going to give you a quick demo.
Alrighty, thank you, Alicia. So before diving right into FastRP, I just wanted to take a second to talk about the data that we're using at a high level. And then also, once we get into it, I'm actually going to take you over into a Python notebook for this one example, because I want to show you conceptually kind of how FastRP explains what's in the graph and do some visualization that'll be easier there. So to get us started with the data set, we are going to use a data set from Microsoft, and it's specifically from Microsoft's news website. And what they did is they took down impressions, and impressions are basically, you can imagine if you go to a news website or really any content website like YouTube, you'll get like a little side panel of different pieces of content that you want to view. An impression for Microsoft News is basically that for different news articles. So they took all of those down, and we're taking a sample of this data, which with the training set and validation set has almost 100,000 users and their click behaviors on the website, whether or not they're clicking different articles. So when we bring that into the graph, there's going to be almost 200,000 nodes, I think, and then a little over 2.5 million relationships. And all I did was I broke it down so that you have a user. There's various different types of click events for news articles, which is another node. And then the news articles are annotated by Microsoft with different categories and subcategories. So categories would be things like sports or health, or food and drink or finance. And then subcategories for sports, for example, would be like baseball, basketball. So just like another level of detail. And then another interesting thing that Microsoft did is they used NLP techniques in combination with Wikidata to extract entities from both the title of the news article and the abstract of the news article. So we also have this wiki entity node. And these could be different types of people, like politicians or famous actors, or really places, different types of states or countries, or associations like a basketball association or different businesses. Really any type of person, place, thing, or organization. So from here, let's go ahead and jump into that notebook and look at FastRP and embeddings in general. So from our notebook, this is pretty basic. It's pretty much the same thing as browser. All I'm doing here is I'm defining the host, database, and the password for my Neo4j database. Some helper functions here. And let me make this a little bit bigger for you so you can see. And then I'm defining this driver, this client here. And I'm going to use that to submit my different commands. And these commands are just the same GDS or Cypher commands you would submit sort of in the browser or the terminal. So the first thing we're going to do to create our embedding, as always, we are going to create our graph projection. And inside of this graph projection here, I am going to take in all of the nodes that we were just looking at in that schema, and all of the relationships. I'm going to take them in undirected, which is going to allow my embedding to basically run both ways, traverse both ways on the graph, which is what I want. I'm also going to take in a node property here, which we're going to use in just a little bit. So this thing I'm calling a wiki encoding. It's from that NLP Wikidata stuff I was talking about earlier with Microsoft. Basically, their encodings have some sort of similarity aspects about them. So if two nodes are similar, these encodings will also be similar. We'll provide some stuff at the end if you want to go into more detail with that. But we're going to bring them in here because we might want to use them inside of our embeddings. And not every node has them, so I'm going to put in a default value of 0 for those that do not include them. Go ahead and give that a run. And then from there, we will run the actual embedding. So this is going to be a FastRP embedding, which stands for Fast Random Projection. The embedding dimension here, I'm going to set at 128. We have our iteration weights, which for FastRP basically define the number of iterations and the weight for each iterations. And it roughly corresponds to sort of how far you're traversing out from each node in the graph to collect weights and create that embedding vector. So here, we're going out 3 times, but we're only weighting the last 2. And this is actually the default configuration for FastRP, including normalization strength. Again, I'm keeping it at default. This is just the value that allows you to adjust to normalize for the total degree centralities in the graph. I always like to include a random seed just so that when I replicate things, I can kind of keep track of where I am. It makes this more replicable. Also, for and this is actually specifically a 1.8 feature, so I'm a little bit ahead of what's generally available. You can still accomplish this with the with 1.7. You'll use something called FastRP extended instead. But basically, I'm taking in those wiki encoding properties, and I'm going to use them to help weight the embedding as it traverses. So basically, it'll include some information about the node attributes in calculating the embedding. So embeddings with similar node attributes, or rather nodes with similar attributes, should also be fairly similar as far as the embedding is concerned. And this is pretty interesting the way this works. Basically, I can tell it to use this Wikidata encoding, and then I can use this property ratio to determine like the percentage of the embeddings to be based on those wiki encoding weights versus just a normal embedding without the node attributes. And here, it's just going to be 0.1, which corresponds to 10%. So 90% of the embeddings will be calculated as normal FastRP, and the last 10% will be calculated using these wiki encoding weights. And I'm going to use the write API. So when I run this command, it's going to write back to the database. It's going to write the embeddings back to the database under this variable name. So we'll go ahead and give that a run. And the great thing about FastRP is that it's relatively quick. Actually, it's very quick. So you see here, it ran in under a second. Again, on a graph with almost 200,000 nodes and a little over 2.5 million relationships. And it tends to maintain really good performance as the graph gets into the hundreds of millions of nodes and even up towards billions and higher. So this is, a really good algorithm for those reasons. That's why it's one of my favorite embedding algorithms that we have with GDS right now. So once that's done, we'll go ahead and just run a simple Cypher query to get our, in this case, we're just going to bring back our news nodes with the embeddings and some other information. We're going to put it inside of a data frame. And what we're going to do with this is we're going to use something called TSNE. And what that does is it's basically a fairly sophisticated dimensionality reduction technique. And we're going to take that 128 dimensional embedding vector and we're going to condense it down into a 2-dimensional vector, which will allow us to visualize it. So TSNE really just gives us a method to visualize what the embeddings look like and how they use the graph structure. So we get our data back, and you see here it's pretty simple. Basically, you get the news ID, you get the summary, which is just the title and the category, and then a column for the category itself. And then this is what the embeddings actually look like. So the vector is cut off here because there's 128 of these numbers. But you can see it's just these arrays of floating point numbers, these decimal numbers. That's what they actually look like. So we'll go ahead here and estimate the TSNE. Again, we're breaking our data. We're sort of summarizing our data into a place where we can actually visualize it effectively. And once that completes, we can go ahead and make the graph for it. So I wanted to show you this because I really think this helps sort of visually conceptualize and get a really good grasp of what these embeddings are doing. So the purpose of the embedding is to express the graph structure in a lower dimensional space. And you can see here basically what I did is I plotted a point for each news node, each embedding, and then I'm color coding these by the category. So you can see the categories here on the side. And you can see that we get these very definite clusters, right? So we get a definite cluster here for sports. We get different sports clusters, different clusters here for food and drink, and for weather, as well as these news clusters. And interestingly, you can learn a little bit about your graph structure just sort of, looking over these. So for example, right, you see these, this talks about Microsoft, Basecamp, Motorola, Google, Uber, and it turns out that this sort of cluster right here is news. And even though it's not reflected directly in the category, this is like news about like tech and startups. Whereas if we go to this cluster about news, you'll see 538. You should see border crisis, some stuff about Democrats. So you see here stuff about voting. So this is actually more of a political news category, a political news cluster. So it's just sort of interesting. So hopefully this kind of helps explain it. These embeddings are really trying to condense down the information in the graph so that it expresses the structure of the graph inside of a lower dimensional space. And that's about it, Alicia, I had for these FastRP embeddings. So I'll go ahead and pass it back to you.
Thank you for that, Zach. So now everyone knows how to use FastRP. Let's talk about Node2Vec. Node2Vec is probably the graph embedding most of you have heard of before if you've heard of graph embeddings. It supports directed graphs, undirected graphs, homogeneous, weighted graphs, and it's basically borrows from how word embeddings work. Node2vec extracts random walks from your graph, starting at each node. Those random walks are kind of like sentences. They provide context windows for each node. And then you learn your embedding based on using those context windows to predict, given a node, what's the next node. What's really cool about Node2vec and the reason people use it is because it can encode either homophily, these two nodes are next to each other in the embedding, or structural roles. So two nodes with similar embeddings have similar structural representations. So Node2vec is used frequently because it's pretty simple to understand, right? I take every node in my graph, I take n random walks, I put those random walks together, I treat them like sentences in Word2Vec. So given a node, what's the next node? I train my skipgram model, it's a type of neural network, take out the hidden layer of that, that's my embedding, I'm good to go. And by tweaking the parameters, I can learn different things. Because of kind of how it works, it's a little slower, it uses a lot of memory, but it's a really good one to get started with. And with that, I'm going to pass it back to Zach for another demo.
Thank you, Alicia. So we're going to go ahead and just run Node2vec right here in the Neo4j console. We're using the same graph projection as we did with FastRP, and some of these arguments are going to be similar as well. So embedding dimension, this is going to be common for all of our node embedding algorithms. We're going to use 128 like we did before with FastRP. Likewise, we're going to have a write property because I'm going to write these embeddings back to the database, and defining a random seed here as well. These two parameters are unique to Node2vec. So the first one, walk length, determines the length of the random walks, and walk per node determines the number of random walks that we do for each node. We'll go ahead and give this a run. So the reason I used custom values here, I cut these down from the defaults. I think they're both 10 in the default configuration. And I did that primarily for performance purposes so I can get this running quickly, kind of in real time. You see here it's still completed in just a little over 12 seconds. But one thing to keep in mind with Node2vec is it is going to take longer to run than FastRP. Arguably, though, it's going to produce higher quality embeddings than FastRP, or slightly higher quality embeddings depending on the graph structure. Once we have this run and this is complete, I will go ahead and show you the results. So doing a similar thing here as we did in that notebook, bringing back the news and getting the news ID and the title and the category with the embedding. I'll go ahead and add a limit here just so that we subsample it and we don't bring everything into the browser. Once we give that a run, we'll get something similar here as we did before. So we have our news ID column, our summary column with the title and the category, a category column, and then you'll see, just like before, we get our embeddings. And these vectors, just like the ones with FastRP, are of dimension 128. So there you go, similar result, different embedding algorithm. So with that, I'll go ahead and pass it back to you, Alicia.
Thanks, Zach. And so on to our last embedding technique, which is GraphSAGE. And what's really cool about GraphSAGE is it uses a different approach to calculating and generating embeddings. So with FastRP and Node2vec, each of those takes your graph as an input and gives you an embedding for each of your nodes as an output. If you get new data in your graph, in order to get an embedding, you have to run them again on your whole graph. GraphSAGE is different because what it lets you do is it lets you take your graph, learn an inductive embedding, or basically a model that, given some data, can generate an embedding. And then when you get new data into your graph, you can apply that model onto those new nodes and get those inductive embeddings without rerunning the whole thing. And so the way GraphSAGE does this is via basically It stands for graph, sampling, and aggregation. And there's 3 steps. There's you sample your graph. So for each node in your graph, you're going to take a sample of your graph, random walks from that central node, out n hops. And at each of those nodes, you're going to collect up the nodes you've sampled and their properties. The next step is the aggregation step, where you're aggregating the properties of neighboring nodes out to that n-hop neighborhood that you've collected up. Then what you do is you're going to fit a model such that nodes that are close together have similar representations, and nodes that are further apart have dissimilar representations. Basically, this is your loss function. And once you fit that model, you now have your inductive embedding, an equation that can take nodes and its neighbors and their properties and generate an embedding for you. So when you get a new data, or when you want to use the data you have, in order to get your embedding, you make a prediction. And the reason that people like this approach, that it's gained traction, is one, it was one of the first techniques to make use of nodes' properties. So instead of just the structure, you're learning the structure and the properties. The other exciting thing, though, the main one, is that it's an inductive embedding. So you generate an embedding on the graph that you have. As you get new data, or if you have an unseen part of your graph, you can take that model and you can apply it to that new data or that different graph and still generate meaningful embeddings. And so let's go back to Zach to show you what that looks like.
Thank you, Alicia. And I'm going to run GraphSAGE again here in the Neo4j browser. Starting with the graph projection, I'm going to make a slight tweak to it and define the property, the wiki encoding up here with the wiki entity to account for the fact that GraphSAGE is a heterogeneous algorithm. Now, I cheated here a little bit. I actually ran the GraphSAGE training before this. And I did that primarily because this, of all the node embedding algorithms, takes the longest to run. So you'll see the API here is a little bit different from Node2Vec and FastRP, and that's because GraphSAGE is a machine learning algorithm. It's a neural network, so it produces a trained model object. So you'll see here I'll define the name of that model object. I will also define some other things here going down into the parameters that we're setting. Let me expand this so you can see it a little bit better, hopefully. I defined the feature properties, the wiki encodings, and GraphSAGE will be smart enough to know that when I define these, they'll just belong to that wiki entity label. The aggregator and the activation function, I'm just keeping it simple here with a mean and a sigmoid. The projected feature dimension is what's responsible for taking the features from all the different node labels and transforming them into a fixed length feature space. I'm choosing a dimensionality here of 10 just to keep things simple. And every node label will get some property because the label itself, that encoding, is one feature for each node. And then it's just the wiki entities that will have this additional wiki encoding to get mapped over. The sample sizes define the sampling for each layer and the number of layers. This is the default with 2 layers and these sampling numbers. Defining a tolerance, defining my search depth here, and keeping, again, with a similar embedding dimension of 128 as with the other 2 that we ran. And you'll see here that this took 560 milliseconds roughly, so I think what's that, like 9.5 minutes to run. So that is one trade-off here to know. GraphSAGE of all the 3 takes the longest, in my experience, to complete, depending on how you configure it. But arguably, because it works naturally with heterogeneous graphs, you could get very high-quality embeddings out of this. So it's just a performance versus accuracy type of trade-off. And just like we did with the other 2, I can go ahead and write the embeddings. Now again, see, because this is a model object, so the API here is a little bit different. I have to call on that model name to write these back out to the graph. I'll go ahead and give that a run. This is writing back to the database. And once this completes, hopefully fairly soon, okay, so that completes, and then we will go ahead and show querying the results. Again, here for this, we'll go ahead and put a limit in of 100 so we don't bring back everything. Same query as with Node2vec and with FastRP, bringing back the news with the title and the category and the embeddings on it. And you'll see here we'll get similar results as before. So you have your news ID, your summary, your category, and then over here we have the embeddings. So these will be 128 dimensionality as well. So with that, I will go ahead and pass it back to you, Alicia.
Thanks, Zach. And so now, hopefully you all know what graph embeddings are, why they're useful, and a couple different ways to calculate them. And so with that background, I'm now going to pass it back to Zach to give us a demo of how to use embeddings for a real-world task, specifically recommendations.
Thank you, Alicia. To go through an example of news recommendation today, we are going to leverage a concept called collaborative filtering. And collaborative filtering is a technique for making automated predictions for a user's preferences based on the activity of other users with similar interests. And for the mind graph, that's really going to boil down to users that have viewed or co-clicked similar news articles. So we'll go ahead and take a look at an example inside of Neo4j. What we're going to do to demonstrate collaborative filtering, first, I'm going to recategorize the news nodes. So some news nodes will have this thing called approximate time, which is a field that I put in, and the news impressions that we're actually looking at, the sample from Microsoft, only occur in a small window in November 2019. And those news articles that have an impression or were included in an impression inside of that window will have this approximate time that I assigned. And news articles that don't but had impressions before that time period will not have this variable. So I'm labeling them recent news and old news respectively. And since the relevance of news tends to fade with time, we're really going to be mostly focused on these recent news articles. So we're going to want to predict similarities between these guys, not necessarily these ones. So the first thing that you might just think of doing inside a cipher is just doing like a few hops in a traversal, right? So I picked a user ID at random here. And you can imagine, right, if I go one hop out to the news that they clicked on, and then I take a second hop out to the users that had clicked on that news, and then a third hop to all those other users what they clicked on, I can get a sense of what this user hasn't looked at yet and what they might prefer to look at based on what these other users clicked. But the issue is that when I run that, you see that this user clicked on 11 articles. There's over 3,000 different users that also clicked on at least one of those articles. And then you end up with over 4,000 potential recommendations. And there's some ways we could kind of filter this down from a cipher perspective. But ultimately, as the data set grows, this kind of technique could become less and less scalable. And it's really a dimensionality problem. And this is where embeddings are going to come in to help solve this. So the first thing I'm going to do is I'm going to create a graph projection. Similar to before, except this time I'm just focusing on the users, the recent news, and I'm focusing on click events and historical click events. Similar to what I was saying before, these click events are ones in impressions inside of our time window where historical clicks occurred sometime in the past. I am going to use a weight property inside of the embedding calculation, and I'm going to weight these more than I'm going to weight the historical clicks. So we'll go ahead and give that a run. And then we'll be able to run our FastRP embedding. Not a huge amount special going on here, picking a pretty standard dimensionality and also using that relationship weight in this calculation. And once that is done, I'm going to run an unsupervised machine learning algorithm called k-nearest neighbor. And what this is going to do is it's going to look at just the recent news nodes inside of that projected graph. and it's going to look at this embedding. And based on the similarity between the embeddings using a cosine distance, it's going to assign this user's also liked relationship if it's high enough. And it's going to write this relationship and the scores back to our original graph. And one of the great things about GDS's implementation of KNN is that we can significantly reduce the computational complexity. So if you're sort of familiar or savvy about this algorithm, you'll know that it has a quadratic complexity normally associated with it. But we have ways to cut that down and make it significantly more performant. So you see we completed the calculation here, and it wrote back relationships a little over 200,000 to the graph. And so what we can do is, now that we have those similarity relationships, we can run a similar query as before, except this time we have to traverse much less graph elements. So same thing here, start out with the user. I am going to consider the historical clicks, going to go to the recent news, and then I'm basically going to take that second hop out, except I get to traverse out on this user's also like relationship that we created. And I'm going to do some filtering to make sure that I don't include the older news that the user also clicked on in that. And from there, I can get a ranked set of news IDs and a ranked set of recommendations for the user. And I can aggregate the scoring from KNN to make sure that I can actually get the most relevant, the most similar news articles to the ones that they've already looked at. And here we go. And now instead of getting over 4,000 results, we get 132, which I personally think is much more manageable. And you can see here, we can get a list with the total scoring based on our KNN analysis. And this is something that can very easily be baked into an API or another microservice that can just put these sorts of recommendations into a presentation layer or from other downstream processing. So I think that's about all I had for this analysis. So I'll go ahead and hand it back, I guess, for Q&A at this point.
Awesome. Thank you for that amazing demo, Zach. That was really good, and I'm sure it really helped folks understand what the heck to do with embeddings. And with that, we've got some resources in case you're curious, want to learn more, you want to get started with Neo4j and graph data science. Check out these links in our bookshelf.
Okay. Thank you, Alicia and Zach. It was a really insightful talks. And a kind reminder for everyone, this was a unique session with no Q&A session. Therefore, if you have any question, feel free to reach out to Neo4j booth or send them an email to the links below. Yeah. Oh, here. Okay. Once again, thank you, Alicia and Zach, for the insightful talks. And for of you guys who want to say thank you for all of these speakers, you can also join to tell your thanks via this link below. And with this, I formally close this session. Thank you. See you on the next session. Have a nice day.